Hey folks, today we're going to do Dalton's Law. So, one more of our gas laws we need to know about. John Dalton came up with the concept of the law of partial pressure. So let's look at what that means. The easiest thing for me to relate to is a bunch of socks. So go home, look in your sock drawer, and see what you find. Okay? Let's say, for example, you went home and you found 5 pairs of black socks, 3 pairs of white socks, and 6 pairs of blue socks. How many pairs of socks do you have? Pause the video, figure it out. Okay, well that was simple. So what you said was I had 5 pairs of black socks, and 3 pairs of white socks, and 6 pairs of blue socks, and that gives me a total of 14 pairs of socks. Okay, that's easy. All you did was add them up. Or if I told you you had 14 pairs and 5 were black and 3 were white, and said how many blue pairs, you could figure out the 6 by subtraction. Okay, that's Dalton's law of partial pressure. He says you've got a total of 14 pairs of socks over here, and you have a bunch of different colors, and you're just going to add them all up. Well, that's the same concept with pressure. He says over here you've got a total pressure, and the total pressure is made up of the pressure of the things that are in it. So let's say this was the pressure of nitrogen, and this was the pressure of oxygen, and this is the pressure of hydrogen, and this is the pressure of carbon dioxide, etc., etc. And you were trying to come up with how much pressure there was, and you said, well, I have this container, and it's made up of nitrogen, oxygen, hydrogen, carbon dioxide, etc. You can add up the pressure of each of the small pieces to come up with the pressure of the whole. So that should make sense. All right. So let's give an example. Let's say you measure a sample of gas, and you know that it contains only oxygen and nitrogen. So there are only 2 things in it, which are oxygen and nitrogen. And the oxygen has a partial pressure of 128 millimeters of mercury. And the nitrogen has a partial pressure of 483 millimeters of mercury. What's the total pressure? Well, you're given 2 pieces, and you know that those are the only 2 pieces in the container. So can you figure out the total? Pause the video, see if you can do it. Sure, well, Dalton's law says your total pressure is equal to the pressure of each individual thing. Now, you've only got 2 things in it, which are pressure 1 and pressure 2, and they're both in millimeters of mercury, so that makes it really easy. So you can take 128 millimeters of mercury, and you can add it to 483 millimeters of mercury, and that will give you 611 millimeters of mercury. That's your answer. Right? Now, since all are in millimeters of mercury, that's really easy to do. Now, you do have to be careful that all of your units are the same, because it's entirely possible I could give you a problem where they're not. So, for example, here you're given a different problem. Again, you're given something that contains only oxygen and nitrogen. The oxygen has a partial pressure of 128 millimeters of mercury, and this time you're given the total pressure, so we're going to have to do subtraction because you're given the total. But you'll notice your total is 16.2 psi. And it's asking you what's the partial pressure of the nitrogen in millimeters of mercury. So pause the video for a second. Think about this on your own. Really, please do this. And see if you can figure this out on your own and solve the problem. Alright, well, there are a couple of ways to do this. You could convert everything to psi and do it in psi and then convert your answer to millimeters of mercury. You could go and convert it to ATMs and then eventually convert to millimeters of mercury. I look at it as, since I'm trying to go to millimeters of mercury and I've got millimeters of mercury up here, I might as well do everything in millimeters of mercury. So the 16.2 psi is my problem, and that's my total. So I'm going to take 16.2 psi and I'm going to do some conversions. Now you all know how to convert, so we're going to switch from psi. Now we can't convert directly to millimeters of mercury, but we can go to atmospheres. And then from atmospheres, we can go to millimeters of mercury. And 1 atmosphere is 14.70 psi, and 1 atmosphere is 760 millimeters of mercury. So when I pull out my trusty calculator and do all of this, I get 837.55, or 838 millimeters of mercury. Now, that's my total, right? And the 128 is the partial pressure of oxygen. So in this case, my total would be my pressure of 1 plus my pressure of my second one. So since I'm trying to figure out the pressure of my second one, my pressure of my total minus the pressure of my first is equal to the pressure of my second. So I take 838. Let's try that again. 838, which is my total, and I subtract the 128, which is my partial, and I come up with 710 millimeters of mercury. And that's my answer of my pressure of nitrogen. All right. So you have to be very careful of conversions. The worksheet's going to give you some practice on that. So when you get to the worksheet, don't do it now. When you get to the worksheet, you'll be able to watch for those. Now, there is a very, very important application of doing this. All right, and this is where we often see partial pressures, and we see it most commonly. Many, many times we do experiments, and they're done over water. And the problem is that water is always evaporating. So when you collect a gas, for example, over water, you're getting some water vapor as well. All right. So in reality, when you go through an experiment and you collect some hydrogen gas or carbon dioxide gas, if you're doing the experiment over water, you're going to be collecting water vapor as well. So here's an example. We take some zinc metal down here at the bottom of this flask, all right, and we've added some sulfuric acid to the flask, and what happens is the zinc metal starts to dissolve. The zinc replaces the hydrogen in this single replacement reaction, and we end up getting hydrogen gas coming off as a byproduct. And so the hydrogen gas is coming up here, and it goes up this little tube, and then comes down this tube, and comes down and goes up that tube, and ends up bubbling up into here. So we have H2 gas. The problem is that this water, this blue stuff here, is water. So it's evaporating. So you don't only have hydrogen gas in there. You actually have hydrogen gas, but you also have water vapor. Now, to you and me, when we walk around school, we call that humidity. All right? It's the amount of water vapor that's in the air. Now, you also know that in the wintertime, there's not as much water vapor in the air because water does not evaporate as quickly in the wintertime because it's cold, so your humidity is much lower. Whereas in the summer, here in Virginia, our humidity is very high. All right. So, what exactly does this mean? Let's see how this works. We have a vapor pressure table for water, and we'll notice down here when it's cold, we have a very low number for our vapor pressure. And as we get warmer in our temperature, so let's say we are down here around room temperature, all right, we have about 21, 22, 23 millimeters of mercury of vapor pressure. Now, what is that? What is vapor pressure? Vapor pressure is, you'll learn more about this in another podcast, but vapor pressure is the tendency of water to evaporate, or the tendency of whatever, in this case it's water, to evaporate. Now, when you get all the way up to 100 degrees Celsius, what happens? Well, water boils. And if we notice way down here on the right, we'll notice that at 100 degrees Celsius, our vapor pressure is, in fact, 760 millimeters of mercury, which means it's evaporating, all of it, all right, if we happen to be at 1 atmospheric pressure, which is 760 millimeters of mercury. All right? So this is talking about how much the water is evaporating. Okay. So let's look at an example. If I collect 100 milliliters of gas in an experiment, some of it was water vapor. Okay, so let's look at this picture again. All right, some of this up here, this is hydrogen gas, but it's also water vapor. All right, so it says the atmospheric pressure today is 759 millimeters of mercury. All right, so let's deal with that. The pressure today is 759 millimeters of mercury. So with 759 millimeters of mercury, that's how much pressure is pushing down on this water. Right? Well, that also means that this used to be full of water, so that means our pressure in here is also 759 millimeters of mercury. That's the way we figure out these experiments. All right. However, our temperature is 23 degrees Celsius. All right. Well, what exactly does that mean? Well, we don't know how much water and how much hydrogen is in here. Right? So what we have to do, I have to go back here and I have to look at, what did I say the temperature was? 23 Celsius. Right? So let's look at 23 Celsius. And at 23 Celsius down here, our vapor pressure is 21.0 millimeters of mercury. All right. So what that means is 21.0 millimeters of mercury of the pressure that's in here is water. Now if the total is 759 and 21 of it is water, that means the remainder has to be this. So we would take 759 millimeters of mercury, we'd subtract 21, right, and we'd come up with 738 millimeters of mercury. So that's the pressure of the hydrogen. The 738 millimeters of mercury plus 21 millimeters of mercury is going to give us our total, which is 759. Again, remember your pressure in here is made up of two things, the pressure of hydrogen and the pressure of water. Based on the temperature today, which was 23 degrees, we know that 21 millimeters of mercury of the pressure in here is water. So the remainder from the 759 has to be 738 millimeters of mercury. That's how we figure out how much pressure of hydrogen there is in that tube. Okay? So, the atmospheric pressure today, so we've just figured that out. Okay, cool. We have to be careful of different units. Remember, sometimes we're not going to always give you the right number of units. Okay, the same units. Right? So, let's say we collect 100 milliliters of gas, same experiment, some of it's water vapor. The atmospheric pressure today is 103.0 kPa. The temperature is 25 Celsius. What's the pressure of the hydrogen gas? Right. Pause the video, guys. See if you can do this. All right, did you figure out our first problem was the 103 kPa, the 103.0 kilopascals? All of our units need to be in millimeters of mercury. Right? So you could actually do the entire thing in kPas if you wanted to. I'm going to choose to do it in millimeters of mercury. So again, if you didn't do that conversion, pause the video, do it now. All right, so let's start here. We have 103.0 kPas. Now we want to convert from kPas to millimeters of mercury. Can't do that. Have to go to atmospheres first. And then from atmospheres, we can go to millimeters of mercury. Now we know that 1 atmosphere is 101.325 kilopascals, and 1 atmosphere is 760 millimeters of mercury. So when I do that math, I come up with a total of 772.6 millimeters of mercury. All right. Well, I know that my temperature today is 25 degrees Celsius. So if I go look at my vapor pressure table, at 25 degrees Celsius, my pressure is 23.7 millimeters of mercury. So my millimeters of mercury is 23.7 millimeters of mercury is my water, and the 772.6 is my total because that's my atmospheric pressure. If I subtract these out, I get 748.9 millimeters of mercury. And that is the pressure that is the pressure of the H2. Okay. Hopefully that helps. Now guys, you could have done the entire thing in kPas. That would have been fine. But then you would have had to have taken this 23.7 that we have there, which is millimeters of mercury, and convert it to kPas. All right, and that would be fine. All right, so that's it, folks. If you have questions, please see us in class. We'll be happy to explain anything. And have a great day. See ya. Bye.